Okay, welcome back. We've been talking about cells, and last time we talked about some general features of cells. We talked about cell theory and then how cells are used to build more complex organisms through a hierarchical organization from cells to tissues to organ systems to complete organisms. So, as what we're going to do now is take a quick look at the size of cells, and cells are small, and so that means we have to use microscopes to look at cells, and so we'll look at some microscopy in a moment. Just to give you a general idea of the scales of things. Scale is hard to grasp in biology. Cells are tiny. There are probably some bacteria who are actually even smaller than 150 nanometers. So give you an idea of a nanometer. If you find a small plastic ruler, and you look at the millimeters on the centimeter side of the ruler, if you look at a centimeter, it's divided into 10 segments, and those are millimeters, obviously. Now, if you take a millimeter and you divide it 1,000 times, that's a micrometer. And so that's about the size of an E. coli in terms of a bacterium. Pretty average E. coli bacterium, about a micrometer long. So that's a millimeter divided into 1,000 pieces. Now, if you take a micrometer and you divide it 1,000 times again, that's 1 nanometer. So 150 nanometers is about 1/10 of a micrometer. So that is tiny. You're not seeing that with the naked eye. You're not even seeing a bacteria with the naked eye. In fact, you wouldn't even see, you just about see the largest human cell, which is an egg, with the naked eye, and that's about 0.2 millimeters. Frog eggs up to about 1 millimeter. So when we're thinking about how big these cells are tiny, and you have trillions of cells in your body that make up you as the complete organism. So we have this wide range. So people always say, Duncan, how big is a cell? And I'm like, well, what kind of cell are we talking about? And what dimension are we talking about as well? So in terms of length or radius, anything from about 150 nanometers up to 1 millimeter is going to be probably the largest you're going to see. Now, even though I've said that, there are some exceptions. In squids, in giant squid which can go up to 1 meter, 2 meters in length, some even bigger than that, there are some axons, some long nerve cells, which can be 1 meter or more long. Now, they still have a very narrow diameter, obviously, but they have grown very, very long. So the question, how big is a cell, is needs a little qualification. But suffice it to say, if we want to look at your average cell, whether it's a eukaryotic cell or a prokaryotic cell, we're going to use a microscope. So let's just quickly look at a microscope, and if you're in lab, you're going to do this in more detail. And you're not in lab, don't worry, you'll take lab at some point in the future and you'll get it then. But just so that you're familiar with what we're looking at in terms of a microscope. Here's a microscope. This is actually the microscope we use in lab. And it's got a number of different pieces. So let's start at the top. These are oculars. So these are ocular lenses, and they, in this microscope, have a magnification of 10x. That means they make something look 10 times bigger. So if we just put the oculars in our eyes and look to something, it's just going to look 10 times bigger. That means a millimeter looks to be about 10 millimeters. So those are the oculars, and then the next, moving down, this is the turret and the head, and this part here is really the business part of the microscope, this part and the part below it. So these are the objective lenses, and objective lenses, they range in magnification power, but these do the majority of the magnification. They range from 10x up to 100x in terms of magnification. So you may see 10x or 20x on a microscope in lab, and then you have a 40x lens and then a 100x lens. So the 10x, 20x, 100x lenses, all they do is they make things 10 times bigger, 100 times bigger if we're talking about 100x. So with the microscopes you guys have in a lab, if you're in lab, and this microscope here, if we used a 100x lens and we're using 10x oculars, that means that whatever you're looking at down the microscope is going to look 1,000 times bigger. So E. coli, which is a micrometer in length, is going to look to be about 1 millimeter in length. And so it's making things much, much bigger, but we're still dealing with very small scales of things. So those are the objective lenses, and then this is the stage, and the sample is on a slide on the stage here. And then there's some mechanics under here, which we're not going to worry about. The light source is down here at the bottom, and this is the adjustment knob for the light source. And then just peeking out around the other side are the focus knobs, and there's a fine focus and a coarse focus, and you'll learn about which one of those to use in lab. So one of the things that a microscope does, that you obviously have seen this before, is it makes things bigger. Making things bigger is important, but if you've got an old styley TV, and you just make it a lot bigger, if you've got an old standard definition TV, or if you've got a giant HD TV, but your internet signal's not strong enough and it's streaming in HD, you know that as soon as you make things bigger, they start getting fuzzy. And so trying to watch something like ice hockey or football or soccer on a giant screen, which is standard definition, it's totally annoying because you can't see the puck or the ball, and so it gets frustrating. Tennis is even worse. So as well as making things big, good microscopes have to make things clear, and this is resolution. It's like going from standard definition to high definition. So let's talk about resolution to start with. So here are two dots. Okay, they're two dots. They're two tiny dots. Okay, just a few millimeters in diameter, and I've magnified them. And so when I've magnified these two dots, it looks like one thing. It looks like actually just a figure eight laid on its side, because as I blew the dots up, they got fuzzier and fuzzier and fuzzier. This is like taking a picture you find on the web and it's 200 pixels by 200 pixels, and then you blow it up to 800 by 800 and you put it into your PowerPoint, and it's all pixelated and granular and you can't see where the edges are. So these two dots are now poorly resolved. And so one of the things a good microscope has to do is it's got to make two things which are actually two things appear as two things. So resolution is this ability to discriminate, that means to tell apart, two objects as the magnification increases. So as magnification increases, things get fuzzier and fuzzier and fuzzier, and a good microscope with good lenses and good optics will actually keep resolution so that you see two objects as two discrete objects. So resolution is actually the minimum distance you can bring two things together. So it's actually measured in a distance, usually in nanometers or micrometers. So it's the distance that you can bring two things together until they no longer appear as two things. So right now on the left, on these two dots, is what we've got is poorly resolved image, basically. Now a good microscope would do this. It would actually make these two dots appear as two discrete structures. They're now bigger, and you can actually see there's a little gap between them. Now I've got this to the point on the screen that if I move them 1 pixel closer together, they appear as one thing. So the two things basically merge together. Even though they may actually be separated by a very, very small distance, the resolution of the computer monitor makes them then look as one thing. So the resolution here of my screen is down to about 1 pixel. That's as close as I can bring two things before they appear as one thing. So that's what resolution is, and you get more into this in microscopy if you take microbiology. So there's a little introduction to resolution. The other thing that you have to do if you're looking at cells down a microscope is you have to improve contrast. If you just took some cells, if you just scraped some cells from the inside of your mouth, your inside of your cheek with a little swab, and you put them on a slide and you put them in a microscope, even with a good microscope, with good resolution, good magnification, you're not going to see anything, because cells, generally speaking, are translucent. You can see through them. And so you have to improve the contrast. And so over on the left here is a low contrast dot that's been magnified, and over on the right is a high contrast dot. And so the one on the right jumps out, it pops. The one on the left is a little bit more subdued, and I could obviously make it more extreme than this, but when I do that, half the people in the room can't ever see the dot. So a lot of the time when you're looking at cells, you have to stain them, and so that gives you contrast. It lets you see internal structures. It lets you discriminate between different cell types, especially with prokaryotes if you're looking at bacteria. And so the whole point of staining and dyeing is to improve contrast. Okay, so that's all about microscopes. Now let's just quickly back up and do a couple of questions. Let's do one question. Let's see what you recall from the last video real quick. So here's a question on cell theory, and then we'll do a question about microscopy, and then we'll wrap it up for this video. So here's a question, and see how you do. Okay, so let's now do a quick question on resolution. Resolution is the hardest thing about this little section. So here's a question on resolution. Okay, so that is it for microscopy and cell size. I want you to keep thinking about cell size. So when we're looking at cells and we're thinking about the functions of cells, I want you to keep the size of these things in context. These are incredibly small structures. That makes what they are doing absolutely amazing. Okay, so we'll pick it up next time. We'll start looking at some structures and functions of cells.